So this video will cover the second derivative test from section 3.4. So we talked about the second derivative and that if the second derivative is greater than 0, that is, if it's positive, then that tells us that we are concave up. We looked at that's concave down. We looked at if we have something that's concave up, the farther we go to the right from left to right, our slope is increasing. So the first derivative tells us about slope. So the second derivative tells us how slope is changing. So the second derivative, how does the slope change? So if the second derivative is positive, our slopes are getting bigger. Conversely, if the second derivative is less than 0, if it's negative, then we're concave down. Because as we go from left to right, our slopes are getting smaller. So we can use this not only to find inflection points, we can also use it to find extrema. If we have a critical point, so a point where the first derivative is 0, the slope is 0, if we are concave down at that point, then that is a maximum. On the other hand, if we have a critical point, the slope is 0, if we're concave up at that critical point, then we have a minimum. So this is what's known as the second derivative test. So if we have a critical point, let's call the critical point x equals c. If we plug that value into the second derivative and we get something that's greater than 0, so positive number, then remember what the second derivative tells us. It tells us we're concave up. But specifically, since this is a critical point, not only are we concave up, but being a critical point, then that is a minimum. On the other hand, if we plug a critical point into the second derivative and we get a negative number, something that's less than 0, then not only does that tell us we're concave down, but since it's specifically a critical point, then that critical point is a maximum. Now, if we plug a critical point into the second derivative and we get a 0, then there's no concavity at that point and the test fails. What that means is we can't determine if it's a maximum or a minimum using the second derivative. So if in that case, use the first derivative test. So second derivative test is nice because you only have to plug in the critical point and not a point on each side of the critical point. But the downside is there's sometimes that the second derivative equals 0 at a critical value, and we're not able to tell if it's a maximum or minimum. So let's look at an example. Let's look at the function x cubed minus 3x squared plus 3. And let's use the second derivative test to find any extrema. So we need to begin by finding our critical points. So our derivative is 3x squared minus 6x, which factors to 3x times x minus 2. So that means our critical points are x equals 0 and x equals 2. 0 makes this 0, 2 makes that 0. So those are the values that make our first derivative equal to 0. Now if we take our second derivative, we get 6x minus 6. So if we substitute our first critical point in for x, we get negative 6. So remember what the second derivative tells us. That tells us concavity. So we're concave down at that point. But remember, this is a critical point. This is a point where we have a horizontal tangent line. So if we're concave down at that point, then x equals 0 is a maximum. Now let's do the same thing for x equals 2. So if we substitute a 2 into the second derivative, we get 6 times 2 minus 6, so 12 minus 6, which is 6. The second derivative tells us concavity, so since that's positive, we're concave up. So since 2 is a critical point, a horizontal tangent line at x equals 2, and we're concave up at that point, then x equals 2 is a minimum. Now remember, these are relative minimums, not necessarily absolute minimum. If we want to find the corresponding x values, we can substitute 0 into the original function, and we get 0 minus 0 plus 3. If we substitute a 2 in, we get 8 minus 4 times 3 plus 3, so we get -1. So that's our relative maximum, that's our relative minimum. If we graph this, then we should be able to verify those results. So if we pull up MathCAD, let's plot this function, and this function x cubed minus 3x squared plus 3. So one critical point at 0, that's our maximum. One critical point at 2, that's our minimum, which is exactly what we saw here. And that kept us from having to plug in a test point on the left side and the right side to find out our slope on each side. So we tested specifically at the critical points, tested the concavity, and that told us where our maximum ends were. Now, while we're at it, let's go ahead and find the inflection point, even though that's not an extrema. So if we have an inflection point, which if we look at our graph, we do, we change concavity, the inflection point will occur when our second derivative is equal to 0. So if we set our second derivative equal to 0, add 6 to both sides, so x equal 1 is our possible inflection point. And since at x equals 0, we are concave down, and at x equals 2, we are concave up, we did change concavity from the left side to the right side of this value, so that is an inflection point. So x equals 1 is here, concave down on the left, concave up on the right. So yes, 1 is an inflection point. So let's look at one more example. Let's look at the function cosine x minus x on the interval from 0 to 4 pi. And let's find the extrema. So maximums and minimums occur at critical points, which is where the first derivative is either 0 or undefined. So if we take the first derivative, minus sine x minus 1, if we set that equal to 0, we can add sine to both sides and get sine x equals 1. So we need to locate all of the values from 0 to 4 pi for which sine is -1. So on the unit circle, sine is the y-coordinate, so the y-coordinate is -1 there. So in the first rotation, that's at 3 pi over 2. And we're going for 2 rotations. So if we're in the second rotation and we're coterminal with that, then we would take that and add a complete rotation to it. which that's 4 pi over 2. So 3 pi over 2 plus 2 pi or plus 4 pi over 2, that'd be 7 pi over 2. So those are the two critical points in our interval. 3 pi over 2 and 7 pi over 2. So now let's use the second derivative test to find out if these are maximums or minimums. So if we take the second derivative, we have a minus, the derivative of sine is cosine, and the derivative of -1 is 0. So if we substitute our values in, we have minus cosine of 3 pi over 2, which cosine at 3 pi over 2 is 0. So the test fails. That doesn't mean it's not a maximum or a minimum. It just means we don't know based on the second derivative test. Likewise, if we put in 7 pi over 2, cosine at 7 pi over 2 is 0, so the test fails again. So in terms of the second derivative test, we were not able to find out if those were maximums or minimums, so we have to go back to the first derivative test. Going back to the first derivative test, we think about 3 pi over 2 and 7 pi over 2. These are the only places in our interval from 0 to 4 pi where our second derivative equals 0. So every place else from 0 to 4 pi, our second derivative is, I'm sorry, not our second derivative. Our first derivative is either positive or negative. So just pick a test point in each interval. So we could put in, let's say, a pi. 1 pi would be in here. 2 pi would be in here. Let's see, this is 8 pi over 2, that's 7 pi over 2. So something just a little bit less than 4 pi. Let's see, 4 times pi is 12, so 12 would probably work there. Let's see what 7 pi over 2 is. 7 pi over 2 is 11. That's a little bit more than 12, so we can use these as our test values. So since the second derivative test fails, we're going to plug these into the first derivative and see if we're increasing or decreasing on each interval to determine if these points are maximums or minimums. So if we substitute pi into our first derivative, sine of pi is 0. So we get a negative. So if our first derivative is negative, that tells us we're decreasing. Remember, the first derivative is slope. So the slope at pi is negative, so we're decreasing. If we put in 2 pi, sine of 2 pi is also 0. So we're decreasing in this interval. And then if we put in 12, we have minus sine of 12 minus 1. So sine of 12, we want to take the opposite side of that, minus 1, and we're negative there. So we are decreasing in that interval. So I went and looked at MathCAD just to check and make sure. If we look at this, we're decreasing here, our slope is 0 here, we're decreasing here, our slope is 0 here, and then we're decreasing here. So let's pull up MathCAD and take a look. Notice I graphed this from 0 to 4 pi, and on that entire interval, we're going down. We can zoom in a little bit. Let's go from -12 to +2. So we're coming down. We have a horizontal tangent line here, but then we're still going down. We have a horizontal tangent line here, and then we keep on going down. So this actually does not have a maximum or a minimum, at least not a relative maximum or minimum in this interval. So the second derivative test failed because at the second derivative, our second derivative was equal to 0, which it looks like we were concave up here and then concave down here. So that was an inflection point. And then we changed from being concave down to concave up here. So we had an inflection point there. So we changed concavity. We actually have another one here, but this point where we tested our critical point, we changed concavity there. So the second derivative is 0. The second derivative was 0 at this other critical point because we changed concavity there. So the second derivative test failed to tell us about the extrema because the second derivative was 0. It was neither concave up or concave down at our critical point. When we did our first derivative test, we were decreasing on both sides of this critical point, so it was neither a max or a minimum. And we were decreasing on both sides of that critical point, so it was not a maximum or a minimum. So for this problem, there are no extrema inside the interval.